Hello everyone, so this is a video on the topic orthonormal basis in Fourier series, and here we'll try to understand first what are orthonormal basis and what are the orthonormal basis function in Fourier series and what are its advantages in Fourier series. Okay, those things we'll try to understand step by step. And then what is Fourier series? We have already discussed regarding the Fourier series in all the previous videos. So if you see any periodic function which are not necessarily sinusoidal periodic function can be expressed as a infinite summation of cosine and sine waves, means if we add many sine and cosine waves having different amplitudes, then we can add them together to give some non-sinusoidal periodic function. Okay, those things we have already discussed. So if you want to see the basics of periodic function, you can go to the first video of this video series and you can see there. So now we are going to understand the orthonormal basis, but before that let me write down that expression for Fourier series first. If we are interested in finding the Fourier series of this function fx, then this Fourier series has been written an cos nx bn sin nx. Okay, so if we remove this summation and write down few terms putting the values of n, a1 cos x plus b1 sin x plus a2 cos twice x plus b2 sin twice x plus a3 cos thrice x plus b3 sin thrice x, like this. Okay, so here we'll see what are the orthonormal basis. Here first we have written down this expression. So now I am coming to another point, and that is regarding the some familiar orthonormal basis we already know. If you remember the representation of a vector in three-dimensional Cartesian coordinate system, so how we can represent, suppose x, y, z, these are the axes. Okay, sorry. So in this system you have been given one vector a, okay, and you have been given to express, write down this vector here. So in terms of Cartesian coordinate system and unit vectors, how we can write, suppose the coordinate of this point is 2 3 1. Okay, so how we can write this vector, 2i cap plus 3j cap plus 1 k cap. Suppose we have been given some another vector, that is this one b, and it is point is 2 3 4. How we can write that vector, b cap b vector 2i cap 3j cap 4k cap. So if you see, to represent different vectors, here we are changing only these coefficients of this I and j and k caps. Okay, this I cap, j cap, k caps, they are remaining same, only these coefficients are changed. So here these I cap, j cap are called basis vectors, and since they are mutually perpendicular to each other, if we take the dot product among them, then we'll have 0, means they are mutually perpendicular to each other. And if we take the dot product among itself, j cap, j cap, k cap, k cap, then we'll have 1. So means their individual magnitude is 1. So this type of basis vector which are having individually magnitude 1 and they are mutually perpendicular to each other, these are called orthonormal basis or orthonormal vectors. Okay, so condition of orthonormality is that first those vectors have to be orthogonal, then they can have only orthonormal, because for orthonormality individual vectors should have magnitude 1. Okay, so these are called orthonormal basis vector because here we are talking in terms of vector. These are orthonormal vectors. So now coming to the Fourier series. Okay, here, so in this Fourier series, twice x sine twice x, cos twice x sine twice x, cos 4x sine 4x, suppose cos 50x sine 50x, all these are orthogonal basis. Here not orthonormal, I have not come to the orthonormality case in the sine and cosine functions till now. Okay, these all are orthogonal basis functions here. So how we can prove the orthogonality of these functions? And here in Fourier series there are there are infinitely many orthogonal basis functions, but in vector, three-dimensional vector, there are only three normal or orthogonal basis vectors are there. Okay, so here, so how we can say about the orthogonal basis or orthonormal basis in terms of function? So in when we talk about the orthogonal basis, orthogonal vector, there we simply do the dot product, and dot product was giving 0. But here, since these are functions and these are periodic functions with the period twice pi, so here we cannot do simply dot product, and because these are not vectors also, so here we have to do the inner product, and inner product is defined like this. Suppose we are talking the orthogonality of cos x sin x, cos x sin x, this is multiplied, not dot product, dx, it is giving 0, means cos x and sin x in this interval, in this period, they are orthogonal to each other. Okay, similarly if we do 0 to twice pi sin x sin twice x dx 0, they are also orthogonal to each other. Similarly, if we write 0 to twice pi cos x cos twice x dx, these are also 0, they are orthogonal to each other. Okay, so in a short form we can write this thing like this: 0 to twice pi sin mx sin nx dx 0 if m not equal to n. Okay, similarly 0 to twice pi cos mx cos mx cos nx dx equal to 0 if m not equal to n, and n 0 to twice pi cos mx sin nx dx equal to 0 for all m n n. Okay, m is equal to n, then also it will be 0. M not is equal to n, then will be equal to 0. So these are the conditions of orthogonality. But what will if m is equal to n? Okay, so means we have to check the orthonormality condition of this cosine and sine functions, and these are the conditions of, these are the inner products of sine and cosine functions, which tell that these sine and cosine functions are mutually orthogonal, and then sine functions are also mutually orthogonal if they are having different frequencies. Okay, means cos x cos twice x cos thrice x, like that. So if you see the condition of orthonormality, it should be like that: 0 twice pi. Okay, if we take the inner product of a function with itself, then cos x into cos x dx, it should be 1. Okay, so if cos x dot cos x dx, it would have been 1, then we say that cos x is a orthonormal function, because cos x and sin x, it has been already proved for orthogonal, and this magnitude of this function has to be 1. And in case of function, we define the property of orthonormality like this: In case of vector, we define like this, I dot 1. Okay, but here interestingly, uh, this one we never get this one 1. Okay, this is what we obtain, this we obtain pi. Okay, so we can make this thing 1 if we divide it by in the both side by pi, 0 to twice pi cos x dx 1. Okay, and we can arrange this thing like this, 0 to twice pi 1 by root pi cos x 1 by root pi cos x dx 1. Now for this function, for 1 by root pi cos x, 1 by root pi cos x, we have got the integral value 1. Okay, so we can say that 1 by root pi cos x, 1 by root pi cos x, and these are orthonormal basis functions. Okay, similarly we can also say that 1 by root pi sin x, this is orthonormal basis. Okay, so here we have to normalize this basis function with this quantity. Okay, so we can make one function orthonormal through the process of normalization. We have seen that, and we have already seen that these cos and sine functions, they are already mutually orthogonal to each other, and we can make them orthonormal through the process of normalization. Okay, now coming to this Fourier series expression, here these sine and cosine functions are there. Those I have already told that they are orthogonal, and we are writing this expression in terms of infinitely many orthogonal functions, which are cos x sin x, cos twice x sin twice x, cos thrice x sin thrice x. For our understanding, we can also, one thing I forgot to mention here, we can also say that this integration of 0 to twice pi 1, okay, cos x dx into equal 0. It means 1 and cos x, or it can be also for sin x. 1 and cos x, they are also mutually orthogonal to each other. Okay, so here since we are there are these components also there, we can say that 1 is multiplied with this. So 1 itself is a orthogonal basis function here if we talk this thing like this. Okay, so now thing is that now we have to compare this expression, Fourier series expression, with that vector representation. Therefore I am making this thing orthonormal. Okay, so if we suppose a1, if we write this thing like this, 1 by root pi cos x plus b1 1 by root pi sin x. If we divide this function with 1 by root pi, then we can make that function orthonormal basis. Okay, but here if you multiply, here you have to divide it by here root pi, here you have to multiply by root pi. Okay, so it will not affect this expression, but point is that we can say that this is a orthonormal basis function here. So now what will be the effect? Now in a Fourier series, this cos x, sin x, this will be not changed. What will change? Only from function to function, these coefficients b1, a1, b1, a2, b2, only these Fourier coefficients will be changed. Okay, so we can say that we can write the Fourier series in terms of orthonormal basis functions, which are 1 by root pi cos x, 1 by root pi sin x, and these Fourier coefficients depending on different Fourier coefficients, this one, we can have the Fourier series. Okay, and we can represent some particular function, like in case of vector, depending on different coefficients of that I cap j cap. Suppose 2 I cap plus 3 j cap plus 4 k cap. Suppose some vector was represented like there. Okay, and this I cap j cap k cap, they are orthonormal basis vector there. So here these are the orthonormal basis function in Fourier series. So same representations, but here infinitely many orthonormal basis functions are there. That is the that way we can compare this Fourier series in terms of this vector representation. Okay, so I hope this concept of orthonormality and orthogonality has been clear to you now, and that is the point. So what is its advantage? So disadvantage means uh, we can take this advantage of this orthogonality and orthonormality of a this trigonometric functions, and we can find the Fourier coefficients. Okay, this a1, b1, a2. For that, we can take this advantage of this orthogonality of this function, and we can find the Fourier coefficient through the process of multiplication in both sides and then integration. So that thing you can find, you can see the second video of this video series, and where we obtain the Fourier coefficients through using this property of orthogonality and orthonormality. Okay, so thank you very much. So if you have any confusions in this explanation, you can ask me in the comment section, and please do subscribe my YouTube channel, and thank you very much.